Hi and welcome back. This section is on storage efficiency. As mentioned before, we will discuss flex clones, compression, deduplication, and compaction. But first we will have a look at some terminology which we want to be familiar with before digging into efficiency. First, flex clones. A flex clone is a writable snapshot copy. So a flex clone is a new volume that is based on a parent snapshot in a parent volume, of course in the same aggregate. Initially, the snapshot creation does not take any space in the aggregate until the client starts to write data to the clone. Flex clones are a licensed feature. The second thing is compression. Compression does what it says it does. It will compress blocks. This compression of blocks can be done in memory, before the blocks get written to disk, which is called inline compression, or it can be done afterwards, when the blocks have already been written to disk. This is called post-process. The main reason for compression would be to save space. This compression is done by compressing compression groups of either 8 kilobytes or 32 kilobytes. Now there's a lot more to be said about this, and we will do that in a second. The third thing is deduplication. Deduplication will try to avoid duplicate blocks. So dedup will either not write duplicate blocks, or it will remove duplicate blocks after they have been written. Inline deduplication is not advised on entry-level systems, because inline dedup benefits from more memory than is available in entry-level systems. We will of course dig into that as well. The fourth item is compaction. Compaction is a new feature. It tries to merge blocks that are smaller than 4 kilobytes into one single 4K block. As you know, Waffle uses 4K blocks. Some collections of data simply do not fill a single 4K block. So you will waste disk space if you write a single K block, because that 1K block will require a 4K block on disk. So you waste 3 kilobytes by storing 1K of data. Compaction will try and gather smaller amounts of data to form one single 4K block, so space is used as efficiently as possible. The volume should be thin provisioned before you can enable compaction. 5 is logical space used. Logical space is the space that the client has claimed in the volume. So if a client, for example, writes a 100 megabyte file, then the logical space occupied by the client is 100 meg. But it may very well be that compression, deduplication, and compaction result in only 10 megabytes of physical blocks. So the client still sees 100 megabytes, but this is not the actual physical space, but it's logical. Then physical space used is the representation of the actual physical blocks that are used in the volume. So if a client writes 100 megabytes and compression, dedup, and compaction manage to reduce that to only 10 megabytes, then the physical space is actually 10 megabytes. This is represented as the efficiency ratio. So logical space may be 100 megabytes and physical blocks may, for example, be 50 megabytes. Then the ratio is 2 to 1. Now the bigger the difference, the greater the efficiency, and so the more space you save. And finally we have buffer cache. Buffer cache is a separate part of RAM where the most recent reads and writes are stored temporarily until new reads and writes arrive and need space in the buffer cache. So this buffer cache is also very important when inline deduplication is enabled, and we will see why in a second. But first let's have a look at flex clones. A flex clone is a writable snapshot copy. Now what does that mean? When you create a volume, this volume has a root inode and clients will write data to the volume. When you create a flex clone, there will be a snapshot, either created manually or automatically, and that functions as the parent snapshot. This snapshot will then be used to create a writable root inode for the new clone. Initially, a clone does not take any space in the aggregate because it only has pointers to the already existing snapshotted blocks via the snapshot. When the client starts to write new data, then new blocks will be allocated into the volume. The flex clone can be made an independent volume by splitting the clone. The blocks that are still referenced by the root inode will then be copied into the flex clone volume and the relationship with the parent will be broken. Now let's have a look at some use cases for flex clones. The first one is sharing blocks. Imagine you have multiple clients or applications that use the same programs or data. Each client or application will run its own data in a personal volume. The space in use by the volumes, in this case, is 5 GB per volume, even though the volumes contain the exact same programs or data. So having 3 volumes with the same data means that you waste a lot of aggregate space. If you'd create a snapshot in the first volume and then use that snapshot as a parent for additional volumes, so clones, then you could potentially save a lot of disk space. In this case, 3 volumes initially only take 5 GB with the 3 of them. Only when the individual volumes start allocating data blocks, then they will start taking more space in the aggregate than 5 GB. Use case 2 would be disaster recovery testing. In a SnapMirror relationship used for disaster recovery, you will have a source volume that is read-write for clients that run production. The destination volume in the cluster is read-only. It is accessible by clients, but always read-only. So you would never be able to simulate that clients fail over to the destination site and continue their work, because the destination is read-only. Now what you could do is create a flex clone of the destination volume and test whether the clients can write to the disaster recovery site, so as to test the failover. Once the test is completed, you can simply delete the clone. And use case 3 would be to restore a VMware virtual machine by starting it from the DR volume. In an ESXi environment, you can run an NFS exported volume as a VMware data store. It will be replicated to the disaster recovery site. If you would lose the source data store or a VM in the source data store, then you could clone the volume, import the virtual machine into the VMware inventory and start it. So actually, the time between losing a virtual machine and accessing it again could be kept to a minimum. Then after the virtual machine was started and clients would be working again, then you could use storage vMotion in VMware to move the VM back to the original data store. And then you could remove the clone. So in the following demonstration, I will demonstrate the first use case, sharing blocks between multiple volumes, and then split the clones. So first we'll check the aggregate space, then we will check the volume space of an existing volume, then we will create 2 clones of that volume. We check the aggregate space again, then we add data to one of the clones, and we will split both clones and see what that does to the aggregate space. Now let's start. So first I'm going to check the available size of an aggregate and the size. So we have 11 GB available and the total size of the aggregate is 14 GB, more or less. Then we have a look at the volume, and I've created a volume called parent, and it has 3 GB it's 3 GB in size, and we have 1.85 GB left. So I created some files in the volume. I've mounted the root volume to /mrt blue. Of course, I've mounted the parent volume, and it has about 1 GB in use, based on a single file called f10. Now I'm going to create a clone, and I say the space guarantee is none, so the volume, the clone, will be thin provisioned, and the junction path is /clone. So now I should have a mounted volume added to my storage virtual machine blue, and as you can see it's clone 1, and when I look in the parent and when I look in clone 1, the same file is available in there because it's the same file based on a parent snapshot. And the space has not changed. Now when I create a second clone, call it clone 2, and the junction path is also clone 2, and the space guarantee is set to none. So that would give me a third directory in that root volume, which would, if I'm not mistaken, it gives me 3 times about 1 GB of storage. So it didn't change the aggregate space. Now when I go to clone 1, copy some data, then that F11 file will be new blocks in clone 1. So now when I look at the space, I will see that I have used up some more aggregate space, which is about 1 gigabyte. So it only starts using space when you start creating new files or new data inside a clone volume. Next thing we do is we will split both clones. And then we'll have to copy all of the data from the parent volume into the actual clone volumes, which will then be separate from the original parent volume. So first we split clone 1, then we split clone 2, and after some time we will have a look at the space in the aggregate again, and we see that we have a lot more space in use right now because of the splitting of the clones. And we have 3 different separate volumes, and we're done.